Let's go. Um, Good morning, everyone. My name is Raphaël Collet. I'm the leader of the framework team, the Python framework team, and I'm mostly in charge of the ORM. And this talk is mostly a presentation as a list of all the things, the major things we changed in the ORM this year. Okay. So you got a scan code if in case you want to ask questions for at the end of the talk. So let's jump in. So what's new? We made a bunch of improvements and optimizations in the ORM itself. By improvements, I mean some of those improvements are kind of new features for developers, and some of those improvements are mostly internal. It's either optimization or kind of some code refactoring that makes the ORM code better to maintain for us. But I'm going to present what directly impacts developers, of course. This is, let's say, this is a long subject since Odoo 13. When we write on records, we call the method write, the updates are not done immediately into the database, and therefore when you want to perform an explicit SQL query, you have to make sure that the updates that you've prepared by former writes are pushed to the database before you actually make your query, especially if those updates directly impact the result of your query. Okay, so essentially you must make sure that the database is synchronized what you may have in memory and that should eventually be in the database before you do the query, and we call that process flushing. So you think at the database at the bottom, the memory at the top, and those three flushing, you push the changes from memory to make sure they're consistent in the database. The database is consistent with that. And the problem is always, okay, if I'm making an SQL query, what should I flush? In Odoo, the only thing you should care of are fields. So essentially, which fields are impacting the result of this SQL query, and those are the things you should push to the database before doing the SQL query. So this SQL query is the one actually made by the if you call search fetch on that domain with a company ID and fetching the field email. So the question is, okay, what should the ORM flush? So in fact, it's not what you should think about, it's even what the ORM has to deal with. Okay, so at the ORM level, the question we ask ourselves is, what do we need to flush? In fact, basically, we need to flush every field that appears somewhere in this query. And I'm going to underline the ones that must be up to date, otherwise they change the result of the SQL query. So, of course, the partner active, the partner company ID, partner share, partner company ID again, the complete name. The ID field actually is always in sync because you cannot change it. So by design, we can ignore that one. And then, so those ones must be flushed. And then there's the one in the select statement, the email. That one actually doesn't need to be flushed because we're fetching it, and actually the fetch operation basically takes the value from the database and puts it in memory or cache, except if there's already a value in cache. If there's a value already in cache, either it's the same value, so it's okay, or that value is actually already more up to date than the one in the database, and in that case we just keep the one in memory. So we don't force updates if they're not necessary. Okay? And the question is, how do we determine all that stuff? And how do we make determining all that stuff, let's say, more robust than it was in the past? In the past, it was implemented with a method called flush search. And flush search was problematic because essentially it was kind of a not part of what compiles the domain, the order by, all those elements of the query, but it was something on the side, and it wasn't really modular. It was completely on the side. It was trying to figure out what the actual code would give as SQL, but was not doing it for real. And there were some bugs, there were some missing flushes that hopefully are pretty rare to be needed, but anyway, it wasn't correct. So in order to figure out how to do that, this is the call graph, a simplified call graph of the main methods that could generate such SQL queries. So I took search, fetch, which are actually very similar, and also read group, which has been refactored actually to use the same components behind the scenes. And essentially, you've got the method underscore search, which basically compiles the domain into the where clause, and also compiles the order into an order by clause. And you have fetch query, which will figure out the select part of the SQL query. And so for the order, we go through a method on the model. So the gray boxes and the pink and one of the field to SQL, they're on the model, and the other are on the environment or the cursor. So the important bit is that we go through a bunch of methods which are on the model, and they all end up into a method which was actually already introduced in 17, which is field to SQL. So it say, okay, I've got that field on that table. Can you give me the SQL expression that gives actually the value of the field? Okay? And then that SQL, it's actually an SQL object. So like the SQL wrapper Denis talked about in the former presentation, that SQL object is then composed with the other stuff to get the final SQL query. And the trick is we can actually use that to figure out what must be flushed. Because every time we compile somehow a field and get some SQL out of it, we know that that field has to be flushed. And potentially, if the expression is more complex, you may know that all that's inside there should be flushed if it's part of a order by or a condition. When it comes from fetch query, actually fetch query will actually call field to SQL by saying it doesn't need to be flushed, by the way. But otherwise, by default, field to SQL knows what to flush. And the way it provides the information is actually thanks to the SQL objects themselves. So the idea is to, as we wrap every SQL together with parameters into an SQL object, we say, okay, that SQL object can have actually some metadata. And when you combine object, all the metadata are collected together. And that metadata is simply the fields that must be flushed. And so for every field that eventually ends up in the SQL query, in the where clause, in the order by clause, they will come up with that metadata to say which fields must be flushed for this part to be correct. And so at the top level, when we got the final SQL query, which is one big SQL object, we simply collect that information. And if I get back to this thing, so the final SQL query is given to execute query. So we introduce a new execute method on the environment, not on the cursor, but on the environment. And when it's provided to an environment, it does three things. It takes the metadata and makes sure it's flushed. Then it executes the query. and actually also it automatically gets the result of the query and returns the result. So you don't have a need of a fetch method. There's another one called execute query dict if you want a list of dicts instead of a list of tuples. Okay, so essentially it performs a fetch all or dict fetch all on the result if the query has a result. If it doesn't have any result, it doesn't return anything. So it's flushed automatically, and therefore everything that's put into an SQL query is automatically guaranteed to be flushed, provided it's provided with the right metadata. Okay, so that method we've introduced, field to SQL, actually enabled a bunch of things, and one of them is to handle non-stored related fields as a plain SQL computation. So non-stored related fields, which means the value of that field is not explicitly in SQL, but if it traverses only many-to-one fields, and it's not subject to access rights for computing its value, so it's compute to do. If those two conditions are satisfied, then you can actually express the value of the related field as, in fact, the value of some field at a few joins away. Essentially, it's implemented with the left joins. And the result is something like this. If you provide that SQL expression, okay, when it returns the SQL expression, it actually can add joins to the query, the final query, okay? So we use that feature, and you can therefore group by a non-stored related field. There's no need to store the field for that anymore. You can aggregate those fields, and you can also order by those fields. And all of that is done with something like 5 lines of code. See? So good refactoring enables new features with very, very small amount of code. And this is what it looks like. Essentially, you've got the join for partner name. It's a related field, so you join by essentially traversing the partner ID relation, and then get the name on the partner parent ID here, alias. Okay. Another thing that we've made since is improving how we flush and we generate updates for flushing the data. So when we've recomputed all the pending recomputations of stored computed fields, and then we determine all the fields that have to be updated on some rows, we generate update statements, SQL update statements. And the update statements used to be batched by, in fact, all the fields and the values that were assigned. And we've improved the batching by enabling, in fact, different records that are not assigned the same values, but they're assigned the same fields. So, in fact, the batching is done now by the set of fields that are being updated. And so a bunch of records that have all the same subset of fields updated can end up into one SQL update. So it's kind of invisible for developers, but for many common cases, it actually enables to make a better batching, in fact, and generate less SQL updates when flushing. Okay, so that's a cool feature. That's a pure optimization. Okay. Next, the next bit, it's not completely part of the ORM, but it's part of the framework. It's the crons. The cron jobs are jobs that are executed regularly and may be triggered actually besides their recurring execution. And what was the problem? We realized that it was actually not easy to detect when cron jobs had errors. You could spot possibly an exception in the logs and things like that, but you had to carefully actually regularly check the logs of the servers to figure out that. And so some of them were just broken, and we had on our production database, for instance, crons that couldn't finish their job because they had a batch of things to do and couldn't proceed all that stuff within their maximum lifetime. So there's a timeout, in fact, for cron jobs, and they couldn't proceed them in time. And actually, as time goes by, they have more and more stuff that still needs to be done. And as there's no progress made at all, those things keep on timing out, and they never complete the stuff. And we've realized at some point that some cron didn't do anything except wasting CPU for several months. And so the one thing we did was to detect when a cron job repeatedly fails, either for an exception or something like that, or a timeout. And when that occurs, the cron, after a certain number of times, the cron is automatically deactivated, so it stops using resources for nothing, and an administrator user is notified for kind of fix that stuff. And the other thing we've made is actually rework a bit many of those cron jobs such that the problem of the timeout is when you have a lot of things to do and you try to do it all in a single SQL transaction. The problem is the bigger the transaction, in fact, the slower it will get. So if you have to update 1,000 records, it's fine. It's actually a reasonably sized transaction. If you start updating 10,000 records, kind of fine. But when you have kind of a million records to update, at some point, actually, Postgres has to store all those things before it can commit. And the idea is that the memory of Postgres is limited. And therefore, once you update or you create or you delete a certain number of records, you can see that the time it takes per record is kind of constant, and then it kind of shifts to a different constant. Because Postgres typically has to use another kind of storage that's an order of magnitude slower than the one before. And so when that occurs, not only is the overall time spent more, but actually for every individual record you add, it's even slower. And so therefore, the good practice is to make sure the stuff is done and don't do too much within one transaction. Try to process a batch that's small enough to be fast. And the trick is to tell the cron executor, I'm not completed yet. I've done some progress. Here's the progress I've done. And this is what we end up with. Essentially, there's a method called notify progress. And essentially, so the cron executor calls the job, and the job is usually a method simply called on a model. And that code can say to the executor, by the way, here is what I made. So you give two numbers, is how much you have done and how much is left to do. If the left to do, the remaining stuff is 0, it means you've completed your job. And therefore, you're ready for the next execution. But so far, you've done your job. If you still have stuff to do, in fact, the executor will simply loop over that job a certain number of times. There's a maximum number of times, but at least it will repeat the job a certain number of times, so you can actually get enough progress until the next time you're executed. Essentially, make progress by making smaller transactions. They will be individually faster, and it really goes faster. So if you have to process something like 100,000 updates or inserts, it's actually way faster to make 10 transactions of 10,000 records than to make one big transaction of 100,000. We've been measuring that. And there really is a large difference. So making smaller transactions is better. Of course, if they're too small, somehow the overhead of the transaction then takes over and slows it down. But don't make transactions too big. And this enables a smooth cooperation somehow between the cron job and its executor. And so the changes we've made essentially is improve the time taken by crons and improve the way errors are occurring and handled to avoid kind of cron that keeps on piling up with stuff not done and just eating resources for nothing. A bunch of other improvements. So I won't talk much about those. They're minor. Essentially, we've kind of pushed to use more and more the SQL wrapper object that we've designed. Those changes you should know. So API changes. We've replaced name search. Name search is now gone. We simply say that when you want to name search, the public method still exists, but essentially it searches on the field display name now. And therefore you use the search method of the field display name. If the field display name is stored in the database, then you just search for that field. If it's not, then you can actually define a domain, and search display name will return an equivalent domain to the condition on display name. The advantage is that name search was tricky to combine when actually part of another search. So name search was used when you say partner ID like something. There was an implicit name search being done there. And as you had an explicit query object, you couldn't combine it with another query or do other kind of optimization. It was tricky. Somehow you were a bit too far in the composition to enable some optimization. So we somehow moved to search display name, which returns a domain, which should be equivalent, of course. And the fact of returning a domain, essentially, when you're processing the domain and you see partner ID like something, you got a domain there. Potentially that domain may be combined with other domains to simplify them and things like that. So this per se does not change much, but it enables actually future domain optimization we want to do in the future. This is a kind of a minor change, but it's common. For instance, so the translation function underscore actually does not work if you use it in a controller, because self is the controller. It's not a record set. It does not have an environment. And therefore, by default, that function didn't work. And also, and this is kind of a Python implementation issue, list comprehension. If you use underscore into list comprehension or dictionary comprehension, it wasn't working as well, simply because the comprehension is executed as a separate stack frame, and that stack frame simply does not contain self. And if it does not contain self, you don't have access to an environment, and therefore the underscore function cannot do. Last bit. This is a refactoring of the checking access rights API. Essentially, we've grouped together the method check access rights and check access rule. And it's now called check access. It always does both. And for two reasons, we realized that developers sometimes use one or the other, but do not systematically use both. So it simplifies the model. Essentially, you say, do I have that access on that record? And second, it enables then us to actually rework the access rights model and keep consistent with the new API. So we'll stop separating permissions with rules and things like that. That's for the future. I'm done here. There is still stuff left on my slides, but I'm going to go to the questions now. If you want to know more, just come to me.
Okay. Unfortunately, we don't have time for the questions. We have to close the talk right now.
Okay,
But
so for the questions, come to me.
yeah, you come to him.
Thank you very much.